16 erasers on this one. No, because I said that's a usually large number.
Something wrong with them. It may not be recycled.
Although I'm not an expert on research. So.
I can tell you there's going to be an exam in this class. Just kidding. All right.
This is what I was telling you. I don't ever see this one definition.
Yeah.
The way you define that.
Sorry, just a weird question. It didn't strike me that I'd be wearing a mask. Is it okay if I take it off for a couple of minutes to eat?
See what?
Is it okay if I take it off for a couple of minutes to eat?
Yeah. If you can go into the
Should I
back
just
corner,
walk out?
that would be.
Sorry.
It's okay. Yeah, just go to the back corner. There's plenty of room, so.
Right, that's what I.
Good. Let's see. Okay, so I think we should start with class. All right, so let me give you a review or summary of the ideas that were covered over the last 2 or 3 lectures. So this is a summary. So here G is a reductive group. And we're working over a field of characteristic P. And gamma, actually, we don't need the characteristic P. Let's just assume it's algebraic response. It works in characteristic 0 too, sort of trivially. So we'll just assume it's just algebraic for this theory anyway. Okay, we're not using Frobenius for anything. So sometimes I'll use gamma to denote the dominant interval waves. All right, so what was one fact that we looked at? So we know that M has a good filtration if and only if, well, when we take xn of G with a module, which I'll denote by delta lambda, of M. This is 0 for all dominant weights and strictly bigger than 0. Okay? And we know that we can actually reduce this just to an x1 statement, x1g delta equals 0. All right, so this was the Donkin-Scott criterion for good filtrations. Here's a 2. If M has a good filtration, then we have a statement that the number of times a filtration factor, remember the nabla refers to the H0, is going to be equal to dimension G. And then what you do is you put the other one in with okay. So 3. So injective pulse. So when I lambda the injective pulse of L lambda. Okay. So and lambda of course is dominant. So then, two things we could say. So we could actually put I lambda in for M over here. So we know that this X will actually vanish for I lambda. So that means I lambda has good filtration. So, so I lambda has a good filtration. And secondly, we have a nice formula for this up here. So if I want to know the number of times lambda appears in I lambda, then it's just the composition factor multiplicity. So this should be a mu. This is a mu. L mu inside of nabla. And this was called Brouwer-Altenburg reciprocity. All right, now, what are the key points in proving a lot of these things? So let me just mention some of the key points. So one key point is that L lambda is the G cycle of nabla lambda. And 2, so all composition factors of nabla lambda satisfy when we say L mu, composition factors of nabla lambda satisfies that mu is always less than or equal to lambda. Okay, and the L lambda appears with multiplicity of 1. I'm not going to write that part up. Okay, so this is a key point. So you actually have control over the composition factor multiplicities here and which ones actually occur in terms of the ordering. And then 3, we have this X criterion, psi G of delta lambda nabla mu this is going to be equal to 0 for I bigger than 0. It's going to be equal to 0 when I is equal to 0 and lambda is not equal to mu. And then it's equal to k when I is equal to 0 and lambda equals to 1. Okay, so these are important properties that we proved for these modules, for the series of the case of rational G modules. Okay, any questions on this so far? Okay, so let me pass these out. Let's see. Anyone else? Did you get one? Everyone get one? Everyone got one? Okay, good. You just take off the gloves. Trying to keep as safe of an environment as possible. Okay, good. All right, so now I want to actually look at this paper. And so let me give you a little bit of background on this paper. Okay. All right, any questions on this? So I want to keep these up here. All right, so I've Xeroxed for you 3 pages of the paper that appeared in Crella in 1988 by Ed Klein, Brian Parshall, and Leonard Scott. Okay, so they're sort of known as CPS. All right, so I have had the fortune of actually working with Brian and Leonard. We've written papers together. I knew Ed pretty well. Unfortunately, Ed Klein passed away. And can you pick? Sorry, can you pick one of these up? Come on. Thank you. So Ed unfortunately passed away in 2012. All right, now I also feel very fortunate because we've talked about these highest weight categories for many years together. So this paper is on finite dimensional algebras and highest weight categories. So they introduced the notion of what's called a highest weight category. Highest weight category. Now, what they did was that they sort of noticed that there are certain categories in algebra which actually come up and that are very similar to one another. So let me give you some examples. So the first category is this category called the VGG category L. So maybe you've taken a class on this. So that's an example of the highest weight category. We'll go over the ideas in a moment. Another category is this category over here, the category of rational G modules. So this category of rational G modules, we'll use a reductive And I think this came up on Friday. So this was something that Jack had in his oral exam. So category perverse sheaves on Gmod B. So it's adorned by the file. And it turns out there's an equivalence of categories with the principal block of category L. So I'm just going to label that by over 0. All right, so let me just direct you to some of the examples. That's on page 92. So let me just say that these examples, some of them are on page 92. Okay, now to be perfectly fair, the highest weight categories were inspired by some other ideas too. So I should give these people credit also. It's kind of a touchy issue, but I'll mention it. So let me mention these other people who had some influence beforehand. So Steve Donkin wrote some papers on generalized Schur algebras. And so, many of the ideas used in this highest weight category theory sort of originate from these papers. There are 2 of them, and they're in the Journal of Algebra. They actually predate this work. So the second attempt was an attempt by Ron Irving who also tried to axiomatize the ideas in the highest weight category, and he called these BGG algebras. So, now, what actually made the CPS work kind of different from 1 and 2? Well, part of the reason that their work became a lot more sort of popularized was there's a connection with finite dimensional algebras. So it turns out that highest weight categories Okay. So whenever you have a highest weight category, it's equivalent to an algebra called quasi-hereditary algebra. Certain types of algebras, whose categories are more equivalent to categories for highest weight categories. So the Klein, Partial, and Scott were able to make this connection with the quasi-hereditary algebras. Okay. I should also mention, we're having in 2022, if you're interested in learning more about this, or even participating in our special session. So we have a tribute to CPS. So there's going to be a tribute to the work of Klein, Partial, and Scott at the AMS sectional meeting, spring sectional. This was supposed to happen this year, but unfortunately it got pushed back. I think you were going to go, right? So anyway, you have another chance. So it's going to be not this next spring, but the following spring. And it's going to be at the University of Virginia. All right, So now what I'd like to do is I'd like to sort of, I'm not gonna write all this out, that's why I have this handout. So I'd like to kind of go over some of the ideas of this highest weight category. Maybe I should keep this up here. Okay, so the first thing is you start off with an abelian category, and you have what's called an interval finite poset of weights. Okay, which means that whenever you sort of bound things from above and below, then it's only going to be a finite set. So you have an interval finite. So let me kind of draw you a picture for the rational category. So remember, your poset's going to be this lambda over here, which are the dominant weights. Okay. Now, this is actually going to be interval finite as if we actually bound from above, because it's already, in some ways, it's sort of bounded from below. So if I take a lambda over here, and if I look at everything which is less, then it's gonna lie in this column over here, and there are only finitely many weights inside that column. Okay, so that gives you the interval finiteness there for this rational G-module category. All right, so let's look at the definition of a highest weight category. So the first thing is you have to have a bunch of simple objects. Okay, so we do have a bunch of simple objects in here, namely the lambdas. So let's think about looking at the category of rational G-modules. All right, so I'm looking at A. I just flip the page here. So let's look at B. All right, so there has to be this collection A lambda such that, well, first of all, we have an embedding of S lambda into A lambda. Here, these are the A lambdas here. Okay. And the quotient has to have composition factors which are less in this order. And sure enough, by 1 and 2, we actually have that. Okay. Now 3, you have to have the irreducible having an injective hull. Okay, fine. I think we actually erased it off the board over here. And the injective hull has to have a good filtration. Well, we actually proved that. Yes, using the Donkin criterion. And it has to have an increasing filtration such that, these conditions actually hold. So if you actually look at the proofs that we did, you can actually verify 1 through 4 with the proofs that we have. Okay, so lo and behold, we have a highest weight category. Right? So if you want to show other things are highest weight categories, these are the basic things you have to prove. I think in PGS they have this X2 criterion, and did you figure out why they have the X2 criterion there? So I'll just kind of explain it. So when you do the proof where you're extending, you're starting a good filtration out, then in order to continue on, you need X2 to be 0. Okay. So you actually don't need all the higher ones to vanish. You just need the X2s to vanish. But in many cases, you could just prove the stronger result anyway. Okay. So I just wanted to point out that these elements, these facts here, having the A lambdas, also having modules which are sort of dual to the A lambdas, is kind of important in the theory too, if you want a very rich theory. So like in category O, you have like the Verma modules, and then you have the dual Verma modules too. So you can play exactly the same game as well. And then the perverse sheaves, you have, what is it, intersection cohomology?
Those are simple.
Those are the simples. And the intermediate ones are the,
You need J lower street of
Okay.
constant sheaves.
right. Okay, so you have those modules, and then you have sort of, you have the analogs of this one and that. Okay. Good. All right, so any questions on this? Okay, so now, let's see, is there anything else I wanted to say in there? I mean, you know, if you look at lemma 3.2, then the lemma 3.2 really follows from this accent we had. And a lot of the things that we proved in lemma 3.2 are sort of things that you prove in the process of proving these facts. Okay, good.
I just have one kind of naive question.
Yeah.
So a lot of what we did, like you were saying, was showing that rational G modules form a highest weight category. Have there been any like major results in the other way? Once you know it's a highest weight category, you get like some really nice properties for free without rational G modules.
So the answer is yes, because actually once you have a highest weight category, then you have various X results working. And that's kind of in this, it's in this lemma 3.2. Okay. So when you axiomatize things, then you get some sort of nice cohomological results too. It's a good question. Let me also mention there more work that Klein, Partial, and Scott have done. What they did was they introduced highest weight categories. Let me write this down because maybe somebody will be interested in this. Okay, so this is the first paper. So this is a paper on highest weight categories and basically quasi-regulatory elements. Okay. Now, what they did was, because a lot of this theory relates to things like intersection cohomology and causalist theory. So in later work, they have highest weight categories with various causalist theories. So basically, these causalist theories, when you add these additional axioms in, then you're looking at various vanishing between X that, let's say, is one of these modules and an irreducible. And you add conditions involving what's called parity vanishing of those things, which is sort of reflective of like the VGG category L. It's actually not known for rational G modules. That was their motivation for doing that. But for BGG category L, the X information is also known. So this is kind of modeled on the category L situation. Okay. All right, good. All right, so now what I want to do is I want to mention some other results for rational G modules that I'm not going to prove these results, but you should definitely be aware of them. All right, so here's the theorem. I'll just first state the theorem, and then I'll give credit to people who have actually worked on this. So the theorem is let V and V prime the rational G model, admitting good filtrations. So then, if I take the tensor product of two modules, it also admits a good filtration. Then V tensor V prime admits a good filtration. All right, so you would think, well, maybe this is clear or obvious, but actually it isn't. If you try using the cohomological criterion, you're not going to get very far, it turns out. So, so the first proofs of this well, it was, so the first proof was probably due to J.P. Wong. And this is for type A. For type A, it's not very hard to prove, actually. But he actually observed how to prove it in type A. And then he had other types. And notice that there's no condition on P here. This happens for every single prime that you want. And then Steve Donkin showed this for all but characteristic 2 and for E7 and E8. Okay, so those are the only cases he couldn't do. He has a big Springer lecture notes which actually works on proving exactly this. It's like 200 or 300 pages long. Okay, and then finally, Olivier Mathieu using a technique called Frobenius splittings. He actually has a general proof. And since that time, there have been other proofs of this fact. So actually, this proof, you have to actually use algebraic geometry. Okay, questions on this? Let me do an example. So let me do an example, please. Okay, so let's just do SLN. So V is the natural representation, which is H0 of omega 1. All right, this is the natural representation. Okay. So if I just take the tensor product of the natural representation, it has good filtration. So we have V tensor V. Take it, let's say V times, which I'll just write up here like this. This has a good filtration. Okay. Good. All right, so now let me mention some other facts. So it turns out that if I take a module which has a good filtration, if I restrict it down to a Levy factor, it's going to have a good filtration too. So here's a theorem. Okay. So let J be subs of the simple roots. So if V is a G module, good filtration. Then when I take the module V and if I restrict it down to this Levy factor, which is also a reductive group, then it has a good filtration. Okay, so good filtrations behave well with respect to restrictions on the levy factors. All right, so here's another theorem. I think this is due to Donkin. So let G be, let's say, the Lie algebra of G. And let's say P be what's called a good prime. All right, so I'm just going to say what a good prime is. I'm not going to write everything out. So the idea is you take the highest root in the root system, the one where the coefficients are the largest, and then you just check whether P divides any of the coefficients. If it doesn't, then it's a good prime. So for example, in type A, the highest root is alpha 1 plus alpha 2 plus alpha 3, all the way up to alpha n. And so no prime divides it, so P is always good for type A. Okay. All right, so then, if I take the symmetric algebra on G, or you can take G or G dual. This has a good filtration. So the group G acts on this thing on G by the adjoint representation, and then it'll act on symmetric powers just sort of by lifting that action. So this has good. Not so obvious, actually. All right, now if I take exterior powers, then I can say the same thing as long as P is bigger than 3h minus 1. So for P is greater than or equal to 3h minus 1. So I think this was observed, well, just an observation. Okay. Then when I take the exterior algebra on G, this has a good filtration. Now, the question is, can you lower the P? And I've asked many people if you can actually do this or not. And no one has given me an answer. So the question I have is, you can go home and try it out. So is this true? Or maybe P good, I don't know. But I still haven't gotten an answer for this, even by asking this question for like over 15 years. All right. So what I'd like to do now is just to introduce you to a topic called polynomial representation theory. So this is actually in Janssen's book. So it's going to use this tensor space over here. So it turns out that when you talk about rational G modules, if you look at polynomial representations, where the representation has coefficients which are polynomials, then it turns out to be a finite dimensional algebra theory. Okay, so let me talk about polynomial representation theory. So I'm just going to work with GLN. So a module for G is polynomial. So this is one definition of this. If and only if the weights have coefficients which are all bigger than 0. So an example of a polynomial representation is like the natural representation. So remember inside of here you have a maximal torus T. And so let's say V is the natural representation for GLN. Okay. So what are the weights? We actually calculated this before. The weights are epsilon 1, epsilon 2, epsilon n. They're just the unit vectors. Okay. And so this is a polynomial representation. So these are unit vectors. So it is polynomial. So naturally, if you take the tensor product of two polynomial representations, you get a polynomial representation because you just add the weights in the tensor product, right? So we have the V tensor D is a polynomial representation. Okay. Now, if you take the adjoint representation, it's not polynomial. So V, which is the adjoint representation, is not polynomial. Because V is V tensor V star. So like, for example, the dual representation is not a polynomial representation because the weights are the negatives of these things. Okay. All right. Okay, so it turns out there's a following theorem. So if you take polynomial representations for G, then this is equivalent to direct sum of E bigger than 0, sort of modules for the Schur algebra SND, where SND is endomorphism algebra, symmetric action, symmetric group acting on the tensor space. All right, so here's the idea. So you have the tensor space over here. The symmetric group acts by permuting the places. Okay, so if you have V1 up to VB or something like that, you have an element here, you just permute the tensors. So this action of sigma D commutes with this reaction of GLN. It's called the double centralizer principle. It's one of the sort of oldest phenomenons in representation theory. So the idea is that you have these sort of commuting actions. And the nice thing is you can sort of take the tensor space and you can sort of think of it as a bimodule for the symmetric group action and the GLN action. And by doing that, you can actually relate the representation theory for the general linear group with representations for the symmetric. Okay, so this is very, very, classic Frobenius or, representation theory. Okay. All right, and it's all sort of, when Frobenius and Schur did this, they did it combinatorially. So what this theory does is it sort of puts it in a more homological type of framework with these endomorphism algebras. So this is called the Schur algebra. And the theorem is that the Schur algebra is a quasi-hereditary algebra. So this is a quasi-hereditary algebra. So its representation theory is the highest weight category. So mod implies that mod SND is our highest weight category. All right, so what I want to do is I want to actually calculate, these are finite dimensional algebras, and we should be able to calculate the dimension of these algebras. And since it's the highest weight category, I can show you how to index the simple modules, and we can write out the standard and the co-standard modules, and we can do all this sort of wonderful stuff. All right. Okay. So here's a fact. So the simple modules for SND. This is a one-to-one correspondence with a set gamma plus ND. So these are partitions of D. Without most n parts. So notice when n is bigger than or equal to d, you're just looking at partitions of d. Okay, so once n gets big enough, then it sort of stabilizes in a certain way. And another fact that you can actually prove is that the dimension of the Schur algebra SND is equal to n squared plus e minus 1, choose n squared minus 1. So there's a nice combinatorial formula which actually tells you the dimension of this. Okay. So the simple modules actually come from simple modules for GLN. So also the simples correspond to L lambda for GLN, such a lambda is polynomial. And it satisfies this condition up here too. All right, so let's do an example. Actually, let me state a theorem first. The theorem comes with the story, okay? All right, so here's the theorem. All right, so the theorem says the following. So SND is a semi-simple. If and only if the following conditions are. Okay, so one, you're in characteristic 0. Okay, so that follows because the group algebra in characteristic 0 is semi-simple, and the morphism algebra of a semi-simple algebra turns out to be semi-simple. Everything's good to go. And then, as long as the group algebra is semi-simple, so like by Moshka's theorem, as long as P does not divide the order of the group, so as long as P is bigger than D, we're okay too, right? So D is less. Okay, so this is actually stated in the literature. All right, so I want to look at an example. Okay, so let's look at this example. So it's the algebra S23, and we'll do some work on this for p equals 2. So the group here is just the general linear group GL2. All right, so I don't know, let's calculate the dimension of this algebra first. Okay. So the dimension of S23 is equal to n squared. So remember, this is n and this is d over there. N squared is 4, d is 3, minus 1, over n squared minus 1, so that's 3. Okay, so I get 6 to choose 3. And last time I checked, it was 20. Agree with that? It's a 20-dimensional algebra. Now, what are the simple modules for S23? They're going to be partitions of 3 with at most 2 parts. Okay? So we're going to have 3 with a partition of 3 with at most 2 parts. We're going to have 2, 1, and that's it. But 1 cubed is a partition of 3, but it has 3 parts. So that's not allowed. Does everyone see? Okay. Now, so if I take, let's see. So let's look at SL, let's look at L21. So when I look at L21, this is a GL2 module. And to get the highest weight as an SL2 module, you just take the difference. Okay. So this is equal to L of omega as sort of SL2 module. 2 minus 1 is 1, and the highest weight is 1 is an SL2 module. And this is going to be the natural representation. So immediately, we know that the dimension of L21 is what? 2, right? Box that off. Now, let's look at L3. Okay, so actually you can think of putting a 0 here if you want. Okay? So then this is going to be L of 3 omega 1 with 3 omega, so I'm taking the difference as an SL2 module. Okay? So as an SL2 module, I'm working in characteristic 2. What's the dimension of L3? For SL2? How do we compute it out?
The twisted tensor formula?
Yes, we use Steinberg's tensor product formula, right? Okay, so good. Very good. So let's do that. So it turns out that L3 is isomorphic to L1 twisted 1 tensor L of 1, 0. Yeah, I guess I can put a 1, 0 here. And again, you can take the difference between the weights. So this is 2-dimensional. This is twist over 2-dimensional representation, still 2-dimensional. So the dimension of L3 is 1. Okay. So we have the irreducible representations we computed their dimensions of. And then, and so if I take 4 squared plus 2 squared, I get 20. All right, so does anyone see any connections here between this 20 and that 20?
Does it have anything to do with the characteristics?
Well, I mean, if I take the sum of squares of the dimensions of the irreducible representations, and it's equal to the dimension of the algebra, what can I say about the algebra?
It's semi-simple.
It's semi-simple, that's exactly right. So this shows that this algebra is semi-simple. There's a little problem, isn't there? Doesn't seem to fit into this, does it? Use 3 here, use 2, right? Well, so the story goes, I worked this example out. I called up Steve Doty. I said, look, there seems to be a real problem here. I worked this out, and here's the example, and lo and behold, it's semi-simple. Okay, he checked it out, everything is semi-simple. And then we actually found a mistake in the proof of this. So it turns out that there's one remaining case that you have to consider. Okay, so we actually got a proof which is now correct. And we published it. It's actually in Janssen's algebraic groups book. And so it's due to us.
Why is this one case so exceptional?
It's just, with low primes, it turns out that low primes give you kind of strange examples. Yeah. So, I mean, we weren't looking for this. I mean, we just happened to find it because we were looking at Schur algebras in general, and we're trying to classify the representation type. So we had to do a bunch of calculations involving quivers and relations for this. And it just so happened that we looked at this one where we calculated this out. And there's this kind of oddball thing that actually happened. I don't know if there's a moral to this story or not. Don't take math for granted. I guess that's moral of the story. So. Okay, so next time I'll actually do another example for Schur algebras where we calculate the structure of the injective modules. They're finite dimensional, obviously, for this because it's a finite dimensional algebra. And we'll actually see how these injectors have a good filtration and everything. And then after that, we'll start moving into the theory that Bob Burrell and May have for higher sheaf cohomology. Good stuff.